Hello teachers, let's move on to chapter 5. And in chapter 5 we talk about integers, and this is the first video for section 5-1, addition and subtraction of integers. So we want to talk about the meaning of integers and their representation on a number line, models for addition and subtraction of integers, and properties of addition and subtraction of integers. Now, what in the world is an integer? So we've talked about whole numbers, counting numbers extensively by this point, and we want to add in the idea of integers, and most people think about integers as positive and negative numbers, and really it's the positive and negative whole numbers. So here's our representation of integers. The set of integers is denoted by a capital I, and I is the set. Notice the ellipsis dots to the left. So that means this pattern continues to the left forever. These are the negative integers. 0 fits right in the middle. And then on the right are the positive integers. And if you look just to the right, starting at 0, 1, 2, 3, 4, 5, those are the whole numbers, right? So we're adding an entire new group of numbers to our list to call them integers, the negative of the whole numbers. So the negative integers are opposites of the positive integers. That's the way you should think about negative integers. They're just the opposites of the positive integers. Negative 4 is the opposite of positive 4, whereas 3 is the opposite of negative 3. So for our very first problem, let's do something simple, and we're going to find the opposite. So we know the opposite of 3 is negative 3. The opposite of negative 5 is positive 5. What about the opposite of 0? Well, it's just 0. You can think about it as negative 0 if you like, but that is just 0. So 0 is the only one that its opposite is the same. And there are those answers just simplified and typed up for you. Now, when you talk about integers, you must be able to talk about absolute value. So this is the first time we've discussed absolute value in this course. The absolute value of a number A, written as, notice these vertical bars, the absolute value of A, that's the way you read that, okay, is the distance on the number line from 0. Now, most people just think about it, it's the positive of whatever's inside there. And that is a true fact of the nature of distance from 0, but absolute value truly means a number's distance from 0. So when you look at the number 4, how far is 4 away from 0? Well, it's 4 units away. So the absolute value of 4 is 4. Well, how far is negative 4 away? Well, the absolute value of negative 4 is also 4. Distance is always a positive or 0 value. Distance is never a negative value. And so, again, when you see absolute value, what that truly means is a number's distance from 0, and picturing the number line is the way to go. And here's the definition of absolute value. Okay, so when you have the absolute value of x, think about it, you don't know the value of x. X could be positive or it could be negative. Now, if x inside is positive, then the absolute value of that is the same as whatever the value is. So if x is greater than or equal to 0, this is true for 0 as well, then the absolute value of x is just x. On the other hand, let's take a look at this. If x is less than 0, why would the absolute value of x equal to negative x, do you think? Well, let's think about an example. The absolute value of negative 3, we know by the definition of absolute value, is negative 3's distance from 0. If we were to look at that on the number line, here's 0, here's negative 1, negative 2, here's negative 3. How far is negative 3 away from 0? Well, we know the answer is 3. And again, we know the fast way to handle that is just basically whatever's in there, make it positive. But really what you're thinking about is the number's distance from 0. Well, what in the world is this definition then? It says the absolute value, if I use that definition, it says the absolute value of negative 3 is equivalent to negative, notice that negative in the front, of negative 3, which look what happens. Negative of a negative 3 should be 3. Now, we have not really reached the part of this lecture where we discuss that, but that's something that you know. Right now, this is just a definition, but I wanted you to realize what's really going on. And when I say negative of a negative 3, what I really should be saying is the opposite of 3, right? Because that's what that negative really means. So again, the absolute value of the opposite of 3 is 3. This is from looking at a number line. But if we use this definition, the absolute value of the opposite of 3 is defined to be the opposite of 3, which is 3. That's what we expect. Maybe I'm making it extra confusing, but that's really the way you should be thinking about this. Now we've got some examples here. We'll do them by hand first, and then we'll look at the results. So the absolute value of 20, remember that's a number's distance from 20 is simply 20. The absolute value of negative 5, or again, the absolute value of the opposite of 5, okay, that is going to equal 5. Remember, the opposite of 5's distance from 0. What is the absolute value of 0? It is 0. Okay. The absolute value of x is equal to 3. We're supposed to evaluate this for x. In this case, we don't, x could be, let's think about it this way, 3, or x could be the opposite of 3. If you check your results, if you take 3 and you plug that in the vertical vars, the absolute value of 3 is 3. In other words, the number's distance from 0 is 3. But the opposite of 3, or negative 3's distance from 0, is also 3. All right, let's do this again for x plus negative 5. So there's two ways we can think about it. We have x plus the opposite of 5 is equal to 1, or by definition, we have x plus the opposite of 5 is equal to negative 1, or the opposite of 1. Now, to solve this first equation, you know what we need to do? We need to add 5 to both sides, and you would get x is equal to 6. Here, we also add 5 to both sides, but in this case, we get x is equal to 4. Now, have we really talked about addition with integers? We really haven't addressed that yet, so there's a little bit more to think about here. But let's run down their answers real quick just to make sure we're matching up. So again, the absolute value of 20 is 20. The absolute value of the opposite of 5 is 5. The absolute value of 0 is 0. The absolute value of x depends on if x is positive or negative. If we don't know, we have, no matter what, the absolute value of x is 3 or negative 3. Both of those answers work. And then x plus negative, the opposite of 5 is equal to 1, or x plus the opposite of 5 is equal to negative 1. To make that true, x would need to be 6 or it would need to be 4, which is exactly what we got before. Okay, now keep in mind we've got more definitions to go through, so this question was almost premature because we've got some more things to discuss, but it's also information that you really already know. We're just thinking about this from a different point of view. Now, something I'm positive that if this is in material that you'll be teaching, you will introduce the chip model to your students. In the chip model, positive integers are represented by yellow chips. Now, the color is not an issue. It could be different for different setups, but we're going to stick with yellow chips for positive and red chips for negative. One red chip neutralizes one yellow chip or makes a 0 pair. Makes sense, right? The integer -1, or the opposite of 1, can be represented by one red chip, or 2 red and 1 yellow, or 3 red and 2 yellow. Again, remember, picture this. red is negative, yellow is positive, and so on. So let's look at some examples of the chip model here. To represent 2, so top left over here, to represent 2, we just have 2 pluses. Another way to represent 2, if you'll see, these, the negative and the positive, cancel each other out. That's like a net 0, and you still have 2 pluses. In the third picture, again, this negative and positive cancel each other out. This negative, positive cancel each other out in green there, and you're left with 2 pluses. And then finally, not the only way to do it, right? But this would still work. Plus negative, plus negative, plus negative. Again, we're left with 2 pluses. All of those represent the positive integer 2. Now, how do we represent the negative integer 2? Well, let's take a look. You could just have 2 negative chips or 2 red chips. You could pair up a positive and negative here, and they have a net 0, and you still have 2 negative chips. We could do a little bit more pairing over here and pair these 2 and these 2. Still, you're left with 2 negative chips. And then here, those pair, and those pair, and you're still left with 2 negative chips. So there's an infinite number of ways with these chip models to represent a particular number, keeping in mind that, again, yellow with the pluses represents a positive number, red with the negatives represents a negative number, and if you have a single positive and a single negative, they are net 0. Now, another way to represent integer addition is the number line model. So the number line model, integers can be represented on a number line, and we use a cat to walk the number line, or you could use a dog to walk the number line. Different textbooks use different objects to walk the number line. Many classrooms have a number line on the floor for their students to walk the number line to represent whole numbers and integers. I think this is a fabulous idea. Here are the rules for walking a number line. Very important here. Always start at 0. And always face the positive direction. So when you're adding, you need to always face the positive direction. If the number is positive, you walk forward. If the number is negative that you're adding, you walk backwards. Okay? So again, addition, always face the positive direction, which is towards the right. If you're adding a positive number, you walk forward. If you're adding a negative number, you walk backwards. Let's take a look at the cat model. You want to? Here we go. So we have a tiny little cat. Notice we started at 0. So right here, if we're going to add 4, we walk 4 to the right. Okay, and then we end up at 4 because we know 0 plus 4 is 4. Start at 0. All right. If we want to talk about a negative 6, we're still facing towards the right, but we walk backwards and get to negative 6. Other models that you might see are the charged field model, which is really just like the chips without the circle. Don't you think? It looks exactly the same. Similar to the chip model, positive integers are represented by pluses and negative integers by minuses. Positive charges neutralize negative charges. So the result here, that neutralizes, 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 and we're left with the 2 negatives, and that represents the negative. So if you'll see, we had 3 positive charges. We had 5 negative charges. This is the same as 3 plus a negative 5, which is equivalent to what's left over, not in green, negative 2. Okay, how about an example? The temperature was negative 4 degrees Celsius. In an hour, it rose to 10 degrees Celsius. What is the new temperature? So if we rose 10 degrees, that means we go up 10 degrees. Let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could highlight that. So we rose up 10 degrees and we end up on 6 degrees. So that represents negative 4 plus 10, which is equal to 6. And we already know this gives us the result of the new temperature is 6 degrees. We could also look at repeated patterns. So here we have a pattern model. It says beginning with whole number facts, things that we already know, right? Things that your students already know, the addition facts. A table of computations is created by a following pattern. So we know 4 plus 3 equals 7, 4 plus 2 equals 6, 4 plus 1 equals 5, 4 plus 0 equals 4. That's a pattern. Notice every time we drop a number that we're adding, make it one lower, then the answer is one lower. So this would imply that 4 plus a negative 1 must equal 3. 4 plus a negative 2 must go one lower and equal 2. 4 plus a negative 3 would equal to 1. You get the picture, right? 4 plus a negative 4 equals 0. And this is a good one with that net charge. 4 plus its opposite should equal 0. 4 plus a negative 5 would be one lower at negative 1, and 4 plus a negative 6 would be negative 2. That pattern continues on. We could even do another one. We could do 4 plus a negative 7. That would equal to a negative 3, correct? And we could also read that as 4 plus the opposite of 7. And that's still equal to negative 3. Just following a pattern of addition facts with whole numbers that we already knew. Now we have a definition of addition of integers. Let m and n be integers as described. So let m and n be integers as described. If m isn't any integer, then 0 plus m equals m, and so does m plus 0. That makes sense, right? That's like the additive identity. When we add 0 to a number, then it should remain the same. And this is true for any integer. It doesn't matter if it's a positive or a negative integer. If m is greater than 0 and n is greater than 0, so we're talking about whole numbers, then m plus n is defined using addition of whole numbers. We already know how to add whole numbers. If m is greater than 0 and n is greater than 0, then, now check this out, the opposite of m plus the opposite of n is really the opposite of just m minus n, the positive values. So anytime the signs match, simply add the two numbers without the signs and the whole answer is going to be negative. If n is greater than 0 and m is bigger than or equal to n, so m is the bigger number here, then m plus a negative n is the same as, notice this is the commutative property, negative n plus m. And this means we could subtract. Remember, m is a bigger number, so that's essentially the answer, m minus n. On the other hand, if n is bigger than m, and m is greater than or equal to 0, then m plus a negative n, so remember which one's bigger? N is bigger. So out of these two, the m and the n is bigger if you're not looking at the negative or the opposite sign. So negative n plus m is going to be negative of n minus m. Basically for D and E, notice what we're doing. We're subtracting the numbers, but we're keeping the sign of the larger valued number when you're not considering the sign. This is a rule you know about integers already. Let m and n be any integers as described. This is a definition of integer addition, this time using absolute values. So it's basically the list I just gave you, but we're using absolute values definitions. Okay, so if m is any integer, then m plus 0 is equal to m, and 0 plus m is also equal to m. Same exact definition we had before. Absolute value not required in that explanation. If m and n are non-negative integers, then m plus n is the sum of the whole numbers m plus n. Also the same as the definition I gave you just a minute ago. Here we go. If m and n are negative integers, so notice this is important, this is new. If m and n are negative integers, then m plus n is just negative of n plus n. Let me give you an example here. If I'm adding negative 3 plus a negative 2, I can add just the, absolute values together. 3 plus 2 is 5, but I keep the negative. That's really what that problem is, or that definition is addressing. Now, if m is a positive integer and n is a negative integer, then m plus n is defined as follows. It depends on which one is bigger. If m is greater than or equal to n, then you do m minus n, okay? And the answer, notice, is positive. Okay? If m is smaller than n, so n is the bigger number, then when you're adding them together, then your answer is negative. And again, I think you're going to feel better if I show you examples here. So for the first one, if we take 3 plus a negative 2, notice what we really do is subtract the two numbers. 3 minus 2 is 1. Since the larger one is positive, my answer is positive. On the other hand, if I have negative 5 plus 2, notice they're opposite signs, so we still subtract and get 3. But the larger of the two absolute values is 5, and that's negative. Therefore, my answer is negative. So integer addition has all the properties of whole number addition. This is very important. So when you're working with integers, you still have the closure property of addition of integers. In other words, if you add two integers together, you get another integer. You have the commutative property of addition of integers. A plus B is equal to B plus A. In other words, you can add in any order that you need to. You have the associative property of addition. Remember, associative property means who you group together. Think about it as who you associate with. And on the left-hand side, A and B are associated or grouped together, and then we add C. On the right-hand side, this time, B and C are associated together. So first you have A, and then you've already calculated B plus C. But it doesn't matter how you do it, you get the same result. And all those are properties of addition of whole numbers as well. Okay? Then we have some extra properties. The identity property of addition. We talked about that just a few minutes ago. When you add 0 to anything, you get the identity, that number. So 0 plus A is equal to A plus 0, which is just A. But now we have a new property in this list, and it is the additive inverse property of integers. So for every integer A, there exists a unique integer, the opposite of A, or negative A. And when you add A and negative A, it's like the charges. They just cancel each other out, and you get 0 as a result. Here we have a theorem. Okay, so there are 3 parts, A, B, and C. So part A, if you have the opposite of A, we talked about this at the very beginning of this lecture. We had a problem that we had to simplify, but now it's official. The opposite of A is just A. In other words, these two negative symbols cancel each other out, or these two opposite symbols cancel each other out to give you A. Part B of the theorem is the addition property of equality for integers. You can add the same number on both sides of the equation. So if you know A equals B, then it is okay to add C to both sides of the equation. And you need this to solve algebra problems. And not just algebra problems, but it helps greatly. And then C, if you have negative A, or the opposite of A plus the opposite of B, it is okay to add A and B together and take the opposite of that result. Okay, so that would be the opposite of A plus B. Now here, let's do some problems. So we've got example 5. It says find the additive inverse. So make sure you read your directions, the additive inverse of each of the following. So that is, you're adding the opposite. So the additive inverse of opposite of 3 plus x is just 3 plus x. Parentheses not required. And there it is typed up for you. Okay. What about the opposite of a plus negative 4? Okay, so it's going to be the opposite. Again, I'm going to need the negative A plus a negative 4 Now we have that rule that says that negative can go inside, so that's going to be the opposite of A plus the opposite of -4, which actually could be written as the opposite of A plus 4, because we had that part A that had the two opposites make back the positive. Typed up, there it is. So you have the opposite of that whole thing, and then that negative goes in with both of them to give you -A plus 4. All right, so let's try this one. So this is going to be the opposite of -3 plus -x. Now this opposite in front can go with each one, so that'd be the opposite of 3 plus the opposite of x. And we know what happens with those two opposites. That turns to 3 plus x. And there it is in less steps. Now, let's talk about some subtraction. So, integer subtraction chip model. The subtraction is a little bit more confusing, but we can do this. So, to find 3, subtract a -2. Okay, so we start with 3. I think everybody's comfortable with that. Notice all the pluses, that represents a +3. Now, if we're going to subtract, which means remove, so take away, if we're going to subtract a -2, we have to have a -2 to subtract. So let me tell you what the fix is. We're going to put in 2 negatives because we need them. But to balance that, we're going to put in 2 pluses. Remember, this is a net 0 right here. So we just added what I have in blue there, which I'm going to erase the blue. We added that in to our system. Okay? And then to take away or subtract means you remove. And so that's why we removed the 2 negatives. And we're left with 1, 2, 3, 4, 5 positive or yellow chips, which means our answer is 5. So if you don't have what you need for a subtraction problem to take away, then you build in 0 by putting the same amount of positive and negative chips, and then you can remove what you want to take away. All right, how about the number line model for subtraction? This is when it gets interesting. Again, picture the big number line that you might have on your classroom floor. Remember, for addition, we always faced the right. If you were adding a positive number, you would just walk forward to the right. If you were adding a negative number, you would walk backwards. You don't turn around, you just walk backwards. Well, when you subtract, you face the other way. So here's the rule. Let me read exactly what it says. Here are the rules for walking the number line. Always start at 0, facing the positive right direction. That's the way you start. If the number is positive, you walk forward. If the number is negative, you walk backward. Subtraction is modeled by turning around and facing the negative or the left direction. And again, keep this in mind, if you are, again, positive, you walk forward. Even when you flip around facing the other direction, and then negative, you walk backwards. Okay, imagine how you could do that. As a matter of fact, make up some examples for yourself so you can really see that happening. It works. It really does work. So, positive. Now, if you're adding positive, again, you walk forward. If you're adding a negative, you walk backwards. If you're subtracting, you face the other way. If you're subtracting a positive number, you walk forwards. If you're subtracting a negative number, you walk backwards. You could also look at the pattern model. So your subtraction facts is really the opposite of your addition facts. So we know that 3 subtract 2 is 1, 3 subtract 3 is 0. Well, what about 3 subtract 4? That's new, but notice how the numbers are going backwards. That must be -1. 3 subtract 5 is -2. And again, you notice the pattern over here. This time we're subtracting smaller numbers. So we start with 3 subtract 2, which we know from our math facts is 1. 3 subtract 1 is 2. 3 subtract 0 is 3. But what about 3 subtract a negative 1? Again, follow the pattern. As your subtrahends get smaller by 1 unit, your answers or your difference gets larger by 1 unit. So 3 subtract a negative 1 must be 4 if it continues to follow the pattern. All right, so I'm at my 30-minute mark, so I'm going to shut part 1 video down for section 5-1, and I'm going to come back and give you yet another definition for subtraction. And it's really an official definition for subtraction.